Ready? Okay, guys, we continue with the second day of activities in the STEM week. Today we have 4 talks and also the photo contest. The photo contest already is closed. Remember that it is at 6:30 outside the great hall. So the contest is going to be taking place there. It's going to be the exhibition and also the winners. So we can begin. This is the first talk that we will have today. So the introduction is going to be made by Laura. So.
Hey, hello, good morning, everyone. Our first talk will be given by Dr. Moreno Andrade. Dr. Moreno Andrade earned his Bachelor of Science in Biology from the Universidad Veracruzana and completed his Master in Science and PhD in Biological Science at the Universidad Nacional Autónoma de México, specializing in biological wastewater treatment. He conducted postdoctoral research at the University of California, Berkeley, and later completed a sabbatical stay at the University of Arizona. He is currently a senior researcher at the Institute of Engineering at UNAM, Curitiba, where his work focuses on the biological treatment of organic waste and the production of value-added products from residual biomass. He is a level 3 member of Mexico's National System of Researchers and has authored more than 100 scientific journal articles. So let's give a big round of applause for Dr. Iván Moreno Andrade.
Thank you very much for the introduction. Well, the waste. Always we saw the waste like a bad guy. But we can use the waste as a substrate, as something with value to transform these very interesting things. Today we'll talk about the anaerobic process that is part of the biotechnological process using microorganisms for generating biofuels. Especially, I will talk about hydrogen and methane and valuable products from organic solid waste. First of all, I want to the page. Work on. I will tell you where I'm coming from, and I'm coming from the National Autonomous University of Mexico. You know, it's one of the largest universities in Latin America. There are around 350,000 students. It's a huge one. But here, everybody knows about the soccer team, the Pumas in Mexico City. But the university, as is national, have different campuses around all the country. In this case, we are part of the campus in Curitiba in Querétaro. And in this sense, we are the Unidad Académica Curitiba, and I'm part of the Institute of Engineering. And what we are working on microbiology, in process engineering, and modeling and automatic control of bioprocess. The idea is to share ideas and work between all the topics to try to solve the environmental process problem. In this sense, the academic unit could be that is part of the Institute of Engineering. The Institute of Engineering is a very huge one. I feel it's the hugest thing at the UNAM. We have around 18 buildings in Mexico City, and we have different academic units, and the one is in Korea where I'm working on. And we are 8 eight researchers at the unit, and a couple of technicians that are working with us, and around 30 students from different levels, from undergraduate to master and PhD, and even some postdoc fellows that are working there. And we have different laboratories. I will show you some pictures about the facilities. We have an auditorium, some classrooms, but the main thing is the laboratories. We have different laboratories that is thematic for have the tools to solve the environmental problems. We have some lab scale pilot lab that we have all here small pilots to recreate huge systems for wastewater treatment. And we have other for physicochemical analysis. That is very typical for environmental engineering lab. We have also the microbiology and molecular lab that is especially in all the stuff of the DNA and try to the microbial identification, characterization, and to check the relationship between all the microorganisms. And we have the instrumental analysis lab. This is the lab where we spend all the money because we have here the most expensive equipment like chromatographs and all the stuff to follow what happened with the environmental processes. Finally, we have some pilots, but more like a semi-industrial scale to try to obtain the results in a more how can I say real experience? Yeah, more real experience. We are working on that. The thing is that we are working in waste biodegradability and the optimization of biogas from different waste, especially hydrogen and methane, and I will talk about that in this talk. Some automatic control, the waste valorization to produce biofertilizers, some waste treatment from various organic waste, municipal, industrial, wastewater, solid waste. And the most important thing, I work there, but I'm not always in the lab. Who is making all the research in practice? The students. We have students for thesis that they are undergraduate, for master and PhD, mainly in environmental engineering. And today I will talk about the history that we are working on the bioenergy production. First of all, the organic solid waste. The organic solid waste is a very, very, very interesting waste that we can work because there's a lack of homogeneity in the organic solid waste. Depending on the characteristic of the solid waste, we can obtain different subproducts. And other thing, we have a lot of these waste. We have more than 2 billion metric tons of municipal solid waste annually produced in the world. It's a huge amount of waste. And of course, this is the waste, total waste, and the organic solid waste represents around the 50% of the waste. If you think, what is the waste that is coming from your house? Usually.
Vegetable peels.
Vegetable peels. What else?
Plastic.
Plastic.
Toilet paper.
Toilet paper. Metal. We have a lot of stuff. PET. We have I don't know. You put something in the refrigerator, and after a while, you say, "Oh, it's not working. Let's go to the waste." The interesting thing is the 50% is organic. This is all the waste, the peels, this all that we are not using anymore from the food. And if we see the 42 percentage of waste that we are disposing from our house is kitchen organic waste. It's a lot. And if we assume the garden of organic waste, that is sometimes when you are making the grass and mowing, you can obtain more than 50% that is organic. The idea is not to see this waste as waste, but see as a substrate, something to transform, and we can use the anaerobic process for hydrogen and methane and other valued products. And we can transform this problem that is going through the landfill, will go through big and a lot of environmental problems, but we can transform into energy. How the anaerobic process works? Do you know something about the anaerobic process? No? There are two metabolisms, the aerobic and the anaerobic. Aerobic what is using oxygen for obtaining energy. We are aerobic, guys, we are aerobic. And anaerobic is in the absence of oxygen. The microorganisms grow in absence of oxygen, and they use basically the substrate to transform into energy, but in the row, they transform the waste into different things. At the beginning, this is the easy way to see the anaerobic process. There are a lot of microorganisms that are following different steps, and it's like a chain. There are some microorganisms that transform the carbohydrates, lipids, and proteins that are in the waste into the monomers like sugars, amino acids, and fatty acid, volatile fatty acid. And this is made by hydrolytic bacteria. After that, there are other processes that names fermentation, where fermentative bacteria transform these sugars and these monomers into volatile fatty acid as acetyl protein, and in the liquid, and in the gas phase, they produce some hydrogen and CO2. After that, other bacteria transform these volatile fatty acid into the shortest fatty acid, that is the acetate, and after that, other microorganisms transform this into biogas, that is a mixture of CO2 and methane. Very interesting. Do you know what is the methane? Or how you can use the methane?
In some farms, they take the methane from cows to power things.
That's it. The methane is a gas that we can use. Everybody use the stove for cooking something. What do you use for as a fuel? A gas. This could be methane, propane, or butane. But this is the easy one, the smaller one, the methane, and we can use it for cooking at house. Other thing, we can use this methane to move industrial motor to transform into electricity. And this is very interesting because we can transform the waste into this fuel and also into electricity or heat. But I will talk. This is the process. What happened in the industrial facility is exactly that what I told you happened in one reactor, a very big tank, and we put all the organic waste here, and the microorganisms transform by the way that I told you into methane. This methane, we can make the purification of the methane to eliminate the CO2 and to use as a biomethane, as a fuel in the gas network. We can transform it by a generator, by electrical energy, or thermal energy. Easy. The problem is that we need to understand how to optimize this stuff and to try to go into the reality. I will start with the first biofuel that we observe here. In the road, we can produce hydrogen. And how can obtain, as I told you at the end, this hydrogen and CO2 is consumed by the archaea and transformed into biogas. But what happens if we heat the archaea? The archaea, at the end, we can obtain the gas rich of hydrogen. The idea is we can separate in two steps the process. First one, we can obtain the fermentation and obtain the hydrogen and all the subproducts, including both the fatty acids, and it can be goes through the methanization and we can obtain the methane. This is very interesting because the hydrogen is a very interesting biofuel. Do you hear about the hydrogen as a fuel? Why is interesting? What do you listen about it? What happens if we burn the hydrogen as fuel? What?
Explodes.
Yes.
Explosive.
Explode, but yes,
But you get water.
no, but explode if you got it, boom. But if you have a small flow of gas, you will have the flame. What you obtain after the heat of the hydrogen?
And water, no water.
Water, because if you have the oxidation of hydrogen 2, and you put some hydrogen, you oxidize H2. Water is very interesting because you don't produce any gas that can pollute the environment. And the other thing, this have a high caloric value. The efficiency is very good and is very suitable for transportation. This is this is made by fuel cells, and it's interesting because this is pushing to look how to make the hydrogen cheap. We usually can obtain hydrolysis by different ways. It's very expensive from electrolysis of water. You put a lot of electrical shock into water and transform it into hydrogen. Very expensive. Or you can transform oil with by the conventional refinery. You can obtain hydrogen. Also, you have pollutants in the way, and it's also expensive. The use in transport is a reality. Now, in San Francisco, there are completely routes that use hydrogen fuels for transportation in the bay. And for example, there are some, Toyota has a car that is now you can they sell it and you can buy it. The problem here in Mexico, what is where we can put in the gas? There is no hydrogen gas station for the cars. For this reason, we don't have this kind of cars in Mexico. But there exists. This is me. And I'm very happy because I drive this. I drove this car that is a BMW 38. It's a very nice car, and they are fueled by hydrogen, and it's wonderful. It's like an electric car, but it's fueled by hydrogen. This is interesting because this say, okay, we have the necessity of have the hydrogen, but the problem is how can obtain it in a cheap way. We can use the process to obtain some hydrogen and to use it for this kind of use. the waste is a little bit tricky because depending on the different place where you obtain this organic waste could be have different characteristics. The idea is all the waste, this is an example, I will talk to you after that, that you can have different subproducts coming from waste. I think that you can imagine the word, but I believe in me. Different products can obtain different kind of subproducts, and in this case, if we are working with food waste as a substrate, with that fermentation, the first step of the anaerobic digestion, we can obtain some biohydrogen, PHA, that is the precursor of the bioplastics. We can obtain biodiesel, biohydrone, hydrogen, and other subproducts in the way that are volatile fatty acid and other very interesting products that is, for example, caprate, that is very expensive in the market, but you obtain in a few quantity. But you can obtain this and this and this and this and this in this change. Then the idea is to take all the subproducts in the way to obtain different economical value from all the way. The problem is, as I told you, the organic solid waste is very variable. This is an example that we are observing in a restaurant or in a house. A lot of pills, some tomato rotten, this kind of stuff. But this little mountain of waste is what we obtained from the recycling facility of the Querétaro, of the Querétaro recycling facility. We can obtain around 40 tons every day of this waste. That is, after the recycling, this is the organic waste that is going obtained at the end. Do you know what happened with all these waste, organic solid waste? It's going to the landfill. This is a problem because the landfill is, well, we have two cells full, we have a new one, will be another mountain of waste there, but the idea is why not to transform all this waste into energy? I will skip this because I want to show you. In the recycling facility, we work with this waste, and at the end, we obtain around 80% of the waste from the facility is organic. This is the idea about the regional market, the Central de Abastos in Querétaro. We have half a ton. We characterize, and everything is around waste from fruits and vegetables. There are a lot of potential to transform into the biogas. And from restaurant, it's the same. You can observe there are a lot of organic waste that the thing is that the microorganisms can consume this and transform into the biohydrogen or methane or other subproducts.
There's, so you have a question.
Yes.
So this works for all sorts of organic, because I'm not a chemist or a biologist, sorry. But there's a lot of services like for compost and these type of things. And you can put vegetable peels, but they tell you cannot put dairy or you cannot put meat and things like that. This works for
You can put everything. You have,
long as it's organic.
yes, as long as you have carbohydrates, you will find great. But if also if you have lipids, so not a little bit, and some proteins will work. Then everything is a very, very strong and robust process that will work.
Okay, sorry for the
interruption. Don't worry, if anyone have a question, just leave it, and I will try to invent something.
Thank you.
The thing is, there's a lot of difference between this waste and at this moment, if I tell you you can transform all the waste to bioenergy, you would say, yes. And if I told you how, you would say, the anaerobic process. And can you show me? You will say, then there is a road that you need to walk to understand how the process is working and how to optimize it. For this reason, I will talk about some of the experiences that the steps that we are following to obtain that we are know now for transforming this into this energy. Especially in my group in the lab. But I feel that all the researchers walk this path. First, we start with some exploratory experiments. I will talk about this. And we start with a little bottles. We put in a little bottles some waste, some microorganisms, and we look what is happening. We follow, we have this system to check the bottles are producing the biogas. We passes this into the to capture the CO2 and to measure the hydrogen. How? It's a very easy, is the flow of gas is with a counter online. But at the beginning, I forgot to put this. We have the bottle, we add a bottle with water inverted, and the bottle of biogas that is produced is going, and with the plasma of the water, we measure how much we have. Very easy, very easy. We start with that. And we make the part as we are. We learn, we are making the undergraduate. If we say, okay, what we need to do is to follow very well the results and to try to understand what is happening. And we can obtain this kind of course. This is every, I don't know, 10 minutes or something like this. We measure how much biogas is producing, and we make the graph. And with this changing the quantity of substrate, the quantity of microorganisms, the different substrate, we can observe the difference in the production of the biogas. It's simple. And you can see, with this residue, we say, the residue number 8, we can obtain around 150 milliliters of hydrogen. Oh, magnificent. But if we see the residue number 11, we can obtain the double. A very easy and cheap way to start to follow this process. If you have this in mind, you can obtain a lot of results, and you can have the base for all what you will work on these topics. Then after that, we say, okay, we can measure how much hydrogen can produce from some residue. Okay, we will try to check and understand what happened with the different parameters that are affecting the fermentation. And we test all of this, the different temperature, reactor configuration, the inoculum that is where the microorganisms that we are using are coming from. Where we took the inoculum for the process, how we can use the different pH, and the good one is the 5.5. The fermentation is in acidic conditions. The particle size of the waste, because we are in a mill, we can obtain these different particle size, the initial total solid concentration, and the hydraulic residence time. This one is very interesting because I will talk about it. How much time remains the waste into the reactor, into the tank that is producing the hydrogen. And we can look, and the different residues have different results. Then we begin with the little bottles, we change into some reactors. This is the most fancy reactors, but also we can use acrylic reactors that is are very cheap. Not too long the use life for it, but this no, not 10, it's 1,000 times cheaper than this. And we can just, we use it and it's not working anymore. And I'll take another one. But in this sense, we have, as I told you, we have now the reactors, we control all the parameters and we can follow what is happening in the process. In this sense, we can control everything and we know and have exactly what is happening with the reactor. This is the second step. Bottles to understand, reactors to understand what happened in the process. And at the beginning, Sonia was a PhD that is working in this to select different HRT, the different times that is passing the waste into the reactor. And the idea was she tested a lot of different changes this time. And the idea was to obtain the optimization of how much the time of the substrate should be in the reactor and how much the microorganisms should be in the reactor. With this, we tested and we checked what is the maximum quantity of hydrogen that we obtain. And after that, there was a surface response graph. And as you can see here, if this is the maximum production of hydrogen. Here we can see a peak. And in this case, at 60 hours of sludge residence time and around, what is this? Like around 16 hours of hydraulic residence time, we have the maximal hydrogen production. This looks easy. You have your reactor, you change the parameters, and you check what is the best. If you are thinking to transform organic solid waste in an efficient way, you can use this and this parameter to obtain the maximal hydrogen production. And other ideas, okay, I have the waste from one place, and what's happening? I mix with other waste different. For example, in this case, we obtain waste from the wastewater treatment plant that is something complicated to treat, and we mix it with food waste. We have a mix, and this is Majo from Colombia who was working on that, and this other guy that also making the PhD, and you will say they are studying, and at the end they are working with the waste. It's just for understand the process. And Majo mix the residues and the mixture ratio. She looks that if she put the organic, the food waste and a little bit of waste coming from the wastewater treatment, she increased a little bit the hydrogen production. It's interesting. Why? And after that, if you take this mixture that can increase the hydrogen production, even you can test the different time, hydraulic residence time, and also you will see that, for example, after hours, you can have a huge difference depending on how much you are working with the reactor from a long time. Then this is interesting. If, as I told you, at 16 hours, you can obtain the maximum hydrogen production. But if you leave a little bit more, the reactor is starting to be slowly and you cannot produce a lot of hydrogen. Then the idea is to understand what is happening with the process, and at the end, this means that if you have a reactor working in that way or working in that way, this reactor will be half of size compared to this for produce the same quantity of hydrogen and to treat the organic solid waste. the money is starting to work here. And after that, we say, okay, who is working on the process? The microorganisms. For this reason, we start to understand what happened with the microorganisms beyond the process. At this moment, all was about the process. But for the microorganisms, okay, we start to edit. In the master degree, she started to working with different strains of microorganisms, try to check if bioaugmentation of them into the reactor increase the hydrogen production. And as you can see with Bacillus subtilis, that is microorganisms that can help with the hydrolysis of the substrate, increase the hydrogen production compared with the other microorganisms. Then the idea is to grow some microorganisms, to put into the reactor, and to increase the quantity of hydrogen. This is very useful for a reactor that is working not too good, not too bad. But if you in this place, let's see, if here we put some of these microorganisms, we increase the quantity of hydrogen that we can obtain, and even triple higher of hydrogen we can obtain. But the problem is, after a while, the quantity of hydrogen decreases. We can put all other shots of the strain, again, the hydrogen is producing more, but after a while, it drops again. Why is happening that? Why you put the microorganisms, produce a lot, and after a while, what is happening? In the waste and on the process, there are a lot of microorganisms. There are a lot of dynamic in the community, and the problem is you put here, and then this is very happy producing, helping to produce the hydrogen. But after a while, all the communities say, okay, where are you? Here, this is my waste. Get out of here. I need this place from the community. And when this place is starting to drop the hydrogen production, you say, okay, we need to check then what is happening with the microbial community. We obtain a lot of values, different value products, as I told you, and one of them is the lactic acid. I will talk what happened with the lactic acid. I discontinued the PhD and say, okay, the organic solid waste is producing a lot of lactic acid. And she worked on that, and she said the red is lactic acid, say, I can obtain hydrogen, and she tests the waste can obtain hydrogen, but also a lot of lactic acid. She can produce lactic acid and in the way to produce hydrogen. And after there are other short routes that can transform in the way the lactic acid into hydrogen and other support. In this sense, we say, okay, there is something happening. And in this case, we take all the microbial community and we start to analyze what happened with the microbial ecology. And Michael, that is for local my group, she works with different of the lactic processes to try to understand what microorganisms are working there and what they are doing. And we have the predicted abundance of functional genes related to hydrolytic, to the lactate metabolism, the hydrogen production, or the organic production. I will not talk more about this idea, but the one thing that I want to transmit to you is that we can understand what the microorganisms are doing and to try to have even some concurrences nets to have the idea what are happening in the correlation between them and who have some syntrophic interaction that can increase the potential of the hydrogen generation. In this sense, we can identify different key microorganisms that can act in the process and to understand what is happening. It's, for example, in this process in particular, Megasphaera Leni is have a large part of the total interaction in this community. Then this is a key microorganism that we have in this kind of residues that we can understand. If we understand that, we can give to Megasphaera the best condition to produce the hydrogen, and with this increase the hydrogen production. It's interesting. We jump from little bottles to process, to understand the process, to understand what is happening in the process with the microorganisms. I was talking about the hydrogen, but remember, all that we can have here, there, some part can we, at the end, after the hydrogen, we can put into methanogenic system and obtain methane. Boom, we can increase the biofuels production. In this case, for the methane, methane is a very, very consolidated and conventional process that has been working from the 70s, from the last century, and is very, very, very robust process. In this case, the hydrogen is a very good solution. The hydrogen is a very interesting new solution, but the methane is the one that is very robust and all you can is all around the world working with this technology. And the idea is what happens if all these organic solid waste from Querétaro and from the state of Querétaro is transformed by the anaerobic process into methane. With this, we have some processes in this reactor, and we check with different combination with how much methane we can obtain from this waste. And if we, at the end, with the results, we have some breakdown about it. If we have some idea of how much of organic solid waste is produced in this state, that is around 250,000 tons per year. If we calculate the methane potential production, we at the end can obtain more than 22 millions of cubic meters of methane per day. If we transform into electricity, we put all the methane to transform into electricity, we can obtain the electric energy for more than 52,000 inhabitants. This is very interesting because with the waste of the state, we can give the electricity at least of 4 municipalities of our state, just with the waste from the state. Maybe it's not too much, but at the end, it's very interesting. There are some industries that all the waste are going through this process to transform into electricity to lower the cost of the overall of the process. This is interesting, but there are other things that we can make. We are between engineers, but we can say Alejandro is a colleague that is working on automatic control, and with a former student of mine, Ulises, we try to make something to control the process to try to increase the biogas production. In this case, the idea is that the reactor, we operate as a sequencing batch reactor, and we follow the sequencing batch reactor, how it works. There we have the reactor for hydrogen or methane production, it's the same. You have the microorganisms and the waste, and after a while, you settle the reactor, the treated waste, or could be wastewater or organic solid waste, you draw the reactor, and you maintain here the microorganisms, and you charge the reactor with more organic solid waste, and react, produce the biogas, and again, and again, and again. The idea of this is to maintain the microorganisms always in the reactor and to increase the potentiality or activity of the microorganisms. The thing is, when we need to settle and draw the phases, we can have the idea to have an automatic way how to stop the reaction and to start with the draw of the reactor. The idea was to follow the biogas production online. As I show you, this is the typical hydrogen or methane production, biogas production, like this with a total at the end. And the idea is when you will stop the reaction, when is the better point to stop the reaction? Here, this is the production of the biogas. If we stop the bioreactor here, what happened? We spend 1, 2, 3, 4, 5 hours, and we can obtain just less of 10% of the biogas. What happens if we stop here at 1 hour? The waste is not treated, and there we have not a lot of biogas. But what happens if we stop at 2 hours here? We can have the best, the freedom, because if we can change it here, we'll start with other cycle and we can obtain the maximum production. The red one is the punctual production of biogas measured, and this is the cumulative. Then we can decide here, and the control makes that. We modify the component expression. This expression is explained this curve, and we add some of this part to take into account the particle that is continue removing. And the idea is, with this, the control is deciding where to stop the process. Again, we test different from a restaurant some ways, and we test in the reactor where the biogas was followed online. And what happened? The control decide when to stop the process and to put the new load of the organic waste. At the beginning, is following the hydrogen or methane production is going and is starting to have a mean. And after that, the model is saying that, okay, there's something that is not working a little bit. There will be continue the hydrogen production, and they will continue, and the control say, okay, this is the point where is the better to
Basically
stop.
measuring like slopes, no, like a rate of
Yeah,
change, and with the
that's
slope,
almost-
if the derivative hits a certain point.
It's looking for a change of the block.
Yeah.
And predicting what will happen at the end of the process. And if you continue with the process, here is where the reactor need to stop. In this graph, we say no, you don't need to stop, you continue. What happens if we discontinue? This is the real volume, in the experimental volume. As you can see, after the total of time, there was just less than 4% of the biogas production. The idea with this is to have something automatic to control the bioreactor. In this sense, this is how in the reactor you can see the production is very stable. This is making some robust, very robust process. In this sense, the reaction time is quite similar after more than almost more than 100 cycles. You can obtain the hydrogen production in a very stable form. Even the rate could be a little bit more after the process is working. Oh, the control is magnificent. In this sense, we change and we going into this industrial process. In this thing, we say, okay, we have the control, we have the idea how it's working, the process, we have how the microorganisms are working, and we have a robust control, and the idea was we can decentralize a pilot. If we have something to control the idea of the control, we can obtain some electricity from the sun. And we don't need to plug in anywhere. And this will control, as I told you, in the lab, we pass from the lab to the industrial scale. And this is autonomous automatic anaerobic digestion handler. And the idea is we can take this and put it in the rural area or pilot experiments in an industry. And it's very interesting. For this, we obtain an award from Package, that is a very huge industry in the wastewater treatment for anaerobic digestion, and the Tinga Foundation. And we are very happy that we have some pictures in the Gazeta now. And the idea is what happened here, why we are here. This me, Julian is working also in microorganism ecology, and Alejandro, as I told you, in control, and we together working on that. The idea is, after that, we continue with the conceptual design of the hydrogen and methane production plant. And Idania Valdez, she is researcher also at the academic unit. She is working on how to have this design of the different plants. And this is an example. There, she had a lot of ideas. And with this case of the lactic acid, how to use and put some reactors to obtain and increase the hydrogen and methane production. And this is one of the conceptual designs that this is reaching the economic viability. And we are very happy also. Then we are, as I told you, jumping from the bottle to the reactor to the industrial pilot and to the conceptual design of the plant. In this sense, the idea is organic waste, lactic fermentation to obtain hydrogen and anaerobic digestion for methane. Easy. Then, after that, reaching the end of the presentation, after the methanization, there is still some residue, liquid and some solid, but there's very interesting also because this can be used as a biofertilizer. Because this, at the end, there are a lot of nutrients remaining in the liquid. There are not too much organic matter and some beneficial microorganisms that can be used in soil. Oh my goodness, after you can obtain energy, but you can obtain also some biofertilizer. This is very interesting. There are a lot of things could be used as a biofertilizer, soil improver, or a periodic. We have some research on all that, but I will just show you a little bit that Ana Laura is also a postdoctoral fellow at my group, and we checked if the digestate can be used as a biofertilizer. We use different residues from different origins, and we pass it by the process, as you can see in a two-way process to obtain it, and we test it into the row of different cucumbers, of lettuce and tomato, and the idea was the different digestates in all the cases help to the seed germination in all the cases. And promoting growth of the size subproducts after, for example, have their 90 days. This is some of the cucumbers with biofertilizer. And the control at this point, there is just starting to have the small products of the cucumbers. And we are testing this in
Greenhouse.
a greenhouse, and we have all the cucumbers. After a while, after we have a lot of different cucumbers, we tested that all is okay with the microbiology, no, and any organic microorganisms there. And after that, we have something like this of cucumbers, and we say, okay, who wants some cucumbers? And everybody goes to home with a bag of cucumbers. For our chile, yeah, that's it. And we work with tomatoes, and the idea is, in all the cases, the steady state are better than even chemical fertilizer, or even from
Compost.
from compost. And we are very happy with this idea. We also have now the knowledge about what happened with the end of the process as a biofertilizer. Then we start an interaction with an industry. Solena is an industry that is working on soil. They are in León, Guanajuato, and they have all the market is going to have a health soil. But they say, can you give us a course about how to produce biofertilizer from organic solid waste? We say, yes, of course, we have now the road for knowledge. We prepare a course. There, the CEO of the company and the process engineering was the only person that took the course. They paid for that. And the idea was all the basis of the anaerobic digestion. And we told the recipe for how it works. It was wonderful. They continue, and after a while, they put a couple of reactors, and they transform organic solid waste into all the process. They don't care about the biogas, about the biofuels. They don't care. They care about the state at the end. And after a while, again, as you can see, Julian and me, we are there. And after a while, they start to solve it, the dyes, as a biofertilizer. And it was, for us, was we are very happy because the idea, we can see that the idea is going to the reality. But after a while, they say, oh, this is a very good product, and we are very successful. And the people is asking us for more of this product. And the capacity is not anymore enough. Then they say, okay, can you help us to increase the production? And we say, yes. And they say, but we have now different reactors, but we don't have a space for put more. We say, control it, and you can increase and have a robust process. And for this reason, we improve the process, the control that I show you for to check when to finish the reaction into the industry. And for this, we have a project from other colleagues from the tech, and as you can see, again, Alejandro is here, and we are working in control. This photo is not very good because everybody is working and I just like yes, but I given them the tools. And at this moment, we are working on the different reactors that they have in the industry and to put the control. And the idea was we put some the controller for the different reactors. And the idea is that the people that is working at the industry, they just control with this panel all the bioreactors, and the idea is check when the process is finishing and change increasing the capacity of the industry to produce it, to generate the product as a bio. The idea this is following online the biogas production, and again, if they are recovering the LDC and using to solve it as a biofertilizer. With this, I am finishing this talk because look this picture. We jump from bottle reactor to understand the process, to have all the way of the process, and to go into the industry to see that this is a real process that can be used and the key of all this adventure is the collaboration. Always the collaboration will be the best part, because you cannot reach this kind of stuff by yourself. You need to have association with other guys, because everybody will help us to understand everything and to go
Really.
further. Yes, of course. Some conclusions and take-home message. The aerobic digestion is a platform with a large number of energy and other value products that can be generated. But as anything in STEM, there's a lot of opportunities. We need to continue to obtain efficient, economically, and optimized process to understand very well what's happening with the microbial community. Very important, and maybe the main interaction between them, and of course the development of ideas to go into practical implementation in field and industry, and at the end the use of organic solid waste, not like waste, but as a substrate, as a biorefinery to obtain bioenergy and other subproducts. With this, I am finishing this talk, and I'm very happy to thanks to all of you to honest fellowship, but and of course all my group, that they are the practical hands that they working on these all that I show you, but not only me, it's a team. Of course, my colleagues, researchers, and the students. They are the force of our research, and thank you for all of you for the attention.
Question, again, you can ask the question in English, it is preferable, but if you feel more comfortable in Spanish, you are also welcome to do it. So any questions, preguntas?
So are there any future plans for implementing this at the household level? And inside that question, would the organic waste from a home for people generate enough waste to generate enough electricity? Maybe not to power it like for the whole day, but paired with solar panels or turbines like a complete system. Could this be part of that?
Yes. This is very interesting because you can scale up the process as you necessity. For example, in house, you can have a very small reactor, like a rotoplas. You get. This can be useful for a house. There are some options, but it's working. For example, there are some places, mainly in rural areas, it is useful because if you have some space, some area for the reactor could be useful, and there are other, I can show you other rearrangement of the process, like maybe biofuels. You listen about it? No. Or there are some reactors that we told like Chinese reactors And then a small one like the rotoplat that could be useful in-house, but you need the space. You have it for a garden or something like this. It's possible to use it. And you can conduct the biogas by tubing for using for cooking. I have some visit that there are some universities, mainly in Asia, there are a lot of universities or places that conduct all the organic waste to transform into biogas, and the biogas is returned into the kitchen to cook the dishes. It's possible. And of course, the other thing is that's it. And in the industry, they, depending on the substrate, they have, you need some modification, but the process is working at the same.
Thank you.
Thank you. Any other question? Otra pregunta? ¿Alguien?
I know that's, well, this process is 100% yield because you're starting from waste and you're arriving to something. Have you checked the cost of this process in the production, mainly for the hydrogen and methane? And how it is changing the cost if there is not separation of the organic waste in the way that we do not do separation here?
Very good question, because, for example, hydrogen is under research.
Yeah.
At this moment, there is not huge plan for biohydrogen production. For the methane, yes, but we are working on the two-stage process and is developing from less than 10 years to now. We are working on that. Could it be, could it not be? Time will say, maybe in a couple of, in the next 20 years or something like this. But for the methane, yes, it's working, and at the huge scale is better because the cost is cheaper. And for example, for the municipal solid waste is the best candidate for using this technology, and going from 100 of tons per day is the returning rate.
Yeah.
It's around between 6 and 8 years. And you can obtain a lot of energy for that, as I show you, for example, for Querétaro. The recycling facility is producing more than 40 tons. Could be very interesting. But yes, at small scale, could be different low-tech technologies that can be used, as I told, the Chinese reactors or methane bank. I don't know how to say. It's for rural areas are very good because it's a very easy process, even that is not too efficient. You can control more or less, and you can obtain the methane.
And in comparison with the biofuels itself, in the normal way that is cows and so on, is there an improvement in this process in comparison?
You mean the
And you mentioned that it is produced normally in
yes, but because the usual one is using the first generation biofuels
Yeah.
is mainly coming from the food.
Yeah.
Corn or the thing is here is cheaper than that because the waste is not
yeah, sure, yeah.
cost, and this is better economical way. But the other one, if at the beginning, for example, Germany is the one that is using a huge quantity of corn to transform into biogas by an anaerobic process.
Yeah.
The idea is to transform it. For example, in Slovakia, no, in Slovenia.
Ljubljana.
In Ljubljana, all the organic solid waste is going to a central facility for anaerobic digestion. And all the organic solid waste of the city is transformed into energy, to heat and energy. And the biogas is returned to the gas net. Some are produced in electricity and some heat, because you can make some heat and electricity power and to use it. But all the organic solid waste in Viviana is used for with this product. And it's a very huge one. It's lovely, the facility.
I have a question, and again, I'm not a chemist. I make a lot of ignorant questions. So the methane, when you're going to use it to produce electricity, it goes, I'm assuming, through a turbine, right?
Yes.
And then it goes where? Is it like a full cycle, or does it go away? Because methane is a greenhouse gas.
Yes, and you will produce carbon dioxide. Yeah, that's the truth.
Okay.
And
You burn it first, or?
you use it like because when I started master degree, all the plant that was from anaerobic digestion, what the objective was to treat the wastewater.
Okay.
And all the biogas, they have a
furnace, right?
Furnace for just to have the flame, and they say the methane is greenhouse gas, but is worse the methane than the carbon dioxide.
Exactly, yes.
And you say, and you transform this into CO2, and you say, oh, we are helping the world. But the idea is you can put into the turbine to transform it into, well, more like a.
Yeah, you take advantage of the energy, right?
And to use as a fuel. And there are the design of this kind of engines are depending on the percentage of height, the methane. There are some modification in the engine, and is working very well.
But it still goes away, right?
Is the CO2 is producing.
Okay.
This other thing. We have a colleague that her name is Carla Munoz, that the idea is to capture the CO2 to transform in other products that could be economically viable, but also to save the environment.
Or can you like pack it underground, for example, if you're
Yes,
doing
of
it in facilities that are like right this?
The majority of the rural facilities usually are underground.
Okay.
Just you can see the small places. That's it.
Okay, thank
Yes, I do have a question. Yeah, this is number one. At the moment of fermenting, is there any chance that we have another product apart from hydrogen or methane that could be potentially harmful in order for it to function like properly for this whole processes of energy?
Yes. This is a very good question, because the organic solid waste, some of them, at the beginning of the hydrolysis, you can produce some subproducts that could inhibit for example, the lemon peel. There are some a component, the name is limoneno. The limonene is when you put it into the anaerobic digestion, the methanogens, they hate this compound. And they say, they don't want to work anymore. The organic fatty acid is starting to have accumulation, and the process is going down and broke. But you need to check some of these kind of compounds that can inhibit the microorganisms, but this is real. It is not too common in organic solid waste coming from household or the municipal solid waste, but in the industry, yes, of course, there are some of these components that you need to take care about. Thank you.
Perfect.
Yep.
About the thing of CO2, I recall you're doing something related with algae, right? Like, is that for trapping CO2 actually?
Yes.
Reactors using algae? Is that for us for the PhD or what?
At the lab, we are, Julian and Herman, they are working with algae to capture some CO2 and transform it into that. The idea is to grow a lot of algae. You can obtain some oil from the algae and you push it, then the oil and other products and the debris, you can put it into an anaerobic digestion and transform it into biogas. But the idea is, this is one of the ideas to obtain biofuels from the third generation. That is capturing the CO2. It is totally true. The algae is the third generation of biofuels. The first one was the food, like corn, and the second generation is all the waste.
Another thing, the reactors, there are no like typical acid reactors, right? They are like outflow.
This one was sequencing batch reactor. All the 90%
Running
today, all was sequencing batch reactor. Of course, we are working with anaerobic large blanket reactors, but I don't show you this. There are different kind of reactors. In this talk was everything in sequencing batch reactor, but there are a lot of different configuration, and this is other thing that is very interesting because you can move the process to obtain different things and to try to have the better way of use. And somebody else? No, are you tired? Do you know about this process? Or is it the first time that you listen about it?
There is another question.
Yes.
After fermentation step, you mentioned that for the production of hydrogen, there is like an inhibition of the methanogens, or like the archaea part, or is it inhibited or like separated the process? How does that work?
Yes, if they are like a change. If this produce something that this is not consuming, will affect the microorganism before because the accumulation, as I told, as you told me that, for example, if you have a lot of fermentation, but the methanogen are not too good, there will be accumulation of volatile fatty acid, and then here is this and this, and the process that should be. How can I say that? There be a balance in all the process, in all the steps to have the good production. And this is very interesting also because the fermentation is, there are a lot of products in fermentation. And one of them is, I think some of you really like this kind of products. The fermentation, what is the first thing that you think when you say fermentation? Alcohol. Yes, that's it. My goodness. Yes, the alcohols are other products that if you change some parameters beyond the volatile fatty acid is going to solvatogenesis, going mainly to alcohols. And for this reason, we are very happy with this process because the fermentation is giving us beer, the brandy, and all the tequila and everything that I know you like.
Just to add something related to your question, since it's your first time to be exposed to many of these terms, such as modified bumpers, biomimetic, and bioreactors, it's an Italian commercial, they say a subject of bioremediation. Experience once a year, we cover these topics such as the modeling of the low curve, talk about reactors and rate of wastewater. Yes. No, and also we collaborate with Dr.
Rather popular course, some of the students that have graduated took it. It's a good convention.
Okay, guys, thank you very much. I think we can give applause to Dr. Moreno. We have the next stop. I'm guessing that the doctors are outside. I've been notified that they were coming. So remember, we have the next one, Dorothy and Dr. Berger for months. Also, yesterday somebody forgot a bag and a computer. They have not been claimed. I'm not sure who forgets a bag and a computer, but somebody did. If you know it, please let me know. Thank you.
Perdóname por todas las interrupciones, pero es que me da mucha curiosidad.